that's one of the reasons why we invited our partners here with ARM and Tanner and SoC Solutions to talk about that next generation of interesting things, the IoT. Okay? So, well, with that, let's get started. Dan?
Thank you, Sean. It's really quite an exciting time in our industry today with the opportunities coming up in IoT. And at the same time, there are a lot of challenges. However, what we're going to talk about today are ways to address the issues, address the market opportunities, and I think that's what DAC is all about. And I think this will provide some perspective from different folks in the industry. And so we're going to start. Each person here is going to give us just a few minutes on their position and their perspective, and then we'll start talking and ask some questions.
Okay, so you
Go
want
ahead,
me
Mike.
to present myself?
Yes.
Or, yeah. Okay, so I'm Mike Eftimakis, IoT Product Manager at ARM. And you want the perspective from ARM about IoT. So, well, what we try to do at ARM is to accelerate IoT. We try to help our customers to build solutions faster. And as you know, we provide IP for processors, but we also have IP for systems. And that allows them, our customers, to build their solutions faster. And we have recently, well, yesterday, we have announced a new program to help our customers go even faster because we have enriched, increased the scope of the Design Start program, which was already
Design Start, is that?
yeah,
Okay.
already announced some time ago to get access to the ARM Cortex M0 processor. And we have extended that program to cover the ARM Cortex M3 processor, which comes with a complete system package around it, and with the capability to try the IP, so be able to download it and try it for free. And then when you go to production, when you want to start producing actual devices using the processor and the system IP, you have a $0 license to start producing. So it's really a great way to help young companies and companies who are not really used to build SoCs to start using our processors to get to a result very quickly, because having the processor and the system IP and including a subsystem that is already pre-built, pre-verified, is a great way to get to a result faster and in the end accelerate the introduction of these new products.
So does that include some software around it as well?
Yeah, that's a good question. And in fact, we you know probably about the Embed initiative in ARM. So we have created a software framework to accelerate IoT as well. And the subsystem that is now in the Design Start program has been, well, we have ported the Embed OS, so all the embedded infrastructure for IoT on this subsystem. So out of the box, it runs with Embed OS. And then you can modify the subsystem. You can modify Embed OS because it's open source, so you can tune it to your needs. Pick only the parts that you want in your system, and then you build your solution, and you can expand it, build your peripherals around it, and you get a solution quickly.
That's great.
Yeah.
Jeff.
Oh. Well, first let me introduce myself. So I'm Jeff Miller. I've been with the Tanner EDA organization for 15 years, but Tanner's much older than that. This is our 30th DAC, so we've been in the market quite a long time, and we're acquired by Mentor 3 years ago, or 3 DACs ago, I guess I would say. And so we've really been able to build out our solutions based on adding in the Mentor point tools. So Tanner provides complete design flows for designing analog, mixed signal and MEMS integrated devices, and now also silicon photonics. So that's really our focus. Now, how does that map to the IoT? If you think about an IoT, IoT is a huge topic area, but to break it down into, first you think of it in tiers. There's the cloud, there's gateways, and then there's the IoT edge devices that actually are the interface between the IoT or the internet and the real world. And the real world is analog, it's multi-physics, and so you need this way of bringing in all of these information from the real world, and that's going to involve sensors and actuators in order to interact with the real world. And that's where these edge devices get so interesting, because they have to be interacting with the real world, they have to interact with the internet, so they have to have a communications interface, usually RF. You have to do some local data processing, so usually you have a processor or some significant digital logic on there, but they also have tremendous constraints on them. They have to be inexpensive, they have to be produced in very high volume, and they have to be very low power. Some of these things have to run years on a single battery, or battery changing will become one of your greatest costs of running an IoT service. And so there's a lot of pressure on these devices to converge, and that means that you have to really customize what you're looking at doing in these devices, and that has really driven a lot of growth and will continue to drive a lot more growth in the semiconductor industry in what we call a custom SoC. And usually that's combining some IP from a company like ARM, but also this special sauce that makes your thing unique. So we're seeing a lot of convergence from the RF guys, adding more digital logic, adding microprocessor cores, adding some analog onto that. And we're seeing the sensor guys add quite a bit of analog signal processing and ultimately processor cores onto the sensors themselves, again, in order to make the IoT real and create these edge devices. So that's really our perspective.
You mentioned silicon photonics. I'm just curious what that entails.
Well, so silicon photonics is sort of a new way of thinking about light interacting with ICs. So normally, it's really in the plane of the IC now instead of like LEDs and optoelectronics type applications. And it's a relatively new field, but there's a lot of very interesting application areas, both in the data center for communication between chips on the same board and between different systems inside the data center. So that's going to be the big first wave of the silicon photonics, is this data center communications. But the second wave coming hot behind it is sensing applications. So we've seen an explosion of research going on into this area for things like structural health monitoring. So embedding sensors that use optical fibers embedded in bridge cables, suspension bridge cables, say, that can monitor the strain on the bridge in real time, and they know when they need to restrict traffic on the bridge because the wind loading is sufficient that they might be running into a problem or something like that. And then, of course, in the health monitoring as well, blood glucose monitors of various types can be done with silicon photonics techniques that can be very challenging to do other ways. So it's a pretty good variety of IoT sensing applications powered by silicon photonics.
That's exciting,
yeah.
Actually. Good. Jim.
Well, thank you. SoC Solutions, in case you don't know, is a small company out of Atlanta, Georgia. We've been in business since 2000. We are an IP supplier, and we're also a design house, and we're the kind of guys that take the ARM design start and the analog portion, and we pull it all together. So we offer subsystems, things like bus infrastructures, multi-matrix buses, but we also do things like flash controllers, serial flash controllers, a lot of things that you'll actually need in building a real IoT product. So most of our focus over the years has been in this low-end Cortex M0, M3 space, and which is just perfect for most of the IoT devices now. So most of the IoT devices, in my opinion, are not going to be these large wearable devices. It's going to be thousands of companies doing thousands of different types of devices, most of them with some kind of custom analog. Most of them that where power management is going to be the main key differentiator between these products. All these products, some of them, for low power, energy harvesting, that sort of stuff, you're powering them up and you're powering them down. It's a lot of issues with how do you manage that with the processor subsystem, with the analog subsystem. So that's kind of what we do. That's our expertise.
That's great. Well, I'm curious too, are we seeing the design activity done by the traditional semiconductor designers?
I think for now we do, but I think going forward, the the business model that's going to drive IoT is not going to be the big semiconductor companies, and because the price pressure on these IoT devices is going to get being pushed lower and lower and lower. So the driving industries are going to be the big data industries. It's going to be the subscription application models, and so these devices are basically enablers for those kind of businesses. So I think to have thousands of different applications and thousands of different designs, you're not going to see traditional IC developers doing it. You're going to see software engineers, FPGA designers, college students. So I mean, it's going to be all over the board. So I'm kind of glad you asked that question. So who's going to train these people? How do we get all these people trained on doing all these different kinds of designs? So I think the industry needs to take more of like an Arduino type approach. They need good reference designs. They need good how to design for dummies. And so I think it's our job to make that whole job easier to be able to enable that new market.
Yeah, so it's really going to require fleshing out the design kits and the reference platforms and things like that.
Well, it's exactly the kind of work we try to do, and we see more and more that just delivering the processor or delivering IP blocks is not sufficient. We need to go a bit further and pre-integrate the IP together to make sure that they work well, and they form the base of a strong foundation for designing and deriving various solutions for IoT or for other applications.
Can you give me an example?
Well, an example is, for example, in IoT we have a strong effort around security at ARM, because we know that security is a key element in IoT, well, to make IoT successful. And unfortunately, security, especially if you want a high level of security, is not easy to get. It's very easy to get it wrong. So what we have done first is to introduce processors that manage security inside the processor. So that's the arrival of trust zone technology to the Cortex-M processors, and that's a very good step. But then we need to also expand this protection throughout the system, and that's what we have done with the secure subsystems, where we implement the security control in hardware in the subsystem, and also we provide IP blocks that can expand this protection around the subsystem and go beyond and protect the complete system. So this is one part. Of course, the other part is the software, and that's where, for example, Embed has many features for security. But we also have software support for security. So that's really something we invest a lot in, to make sure that we make it as simple as possible for companies to integrate that in their design, even if they are not security experts.
What do you think, Jeff?
Well, I think the security topic is a huge and important one, and I think one of the things that's most important to remember is that it's everyone's responsibility across the whole design chain. So a lot of people can think, oh well, it's security's not my problem; it's the next guy up the chain's problem. But we've seen exploits that exploit MEMS sensors actually being exploited by virtue of vibrating them with particular patterns from the phone's speaker, and actually being able to take control of the phone through the MEMS sensors. And so there's this it has to be across the board, and it has to be a defense in depth. So you can't just have you need these technologies to compartmentalize things, but that doesn't abdicate people in the individual compartments in those secure areas from also taking responsibility for their own piece of the security. So it has to be designed in from day one, and it has to be everyone's responsibility.
Is there a perception that security used to be or can still be handled with just software?
Oh well, no. It's a combination of different factors. And for example, if you want to support over-the-air update of your device, which is key for security, because you can't stay with a fixed software, fixed firmware in your device and be happy for 10 years, because during this period, something will happen, some new exploits will be discovered, etc. So you have to enable firmware over-the-air update. The problem is that if you want to make sure that you can do it, you need to support it with hardware. For example, you need to have a larger memory area to be able to store your new software while still running the old one. You need to make in your device the capability to have this update. Also, the security features that make sure that once you have updated, you cannot go back to the previous version. And so all of these features require some hardware support. And if you don't build into your design from the start, then you have a problem. So that's
Right, you can't go back
really,
and
yeah,
add
that's
it back
really
into the
important.
chip later,
Yeah.
obviously.
I would like to add though the whole security notion of just being in hardware just contained right on the chip is just a very small portion of the whole security problem. You know, just encryption it certainly is necessary, but you know, you need to be able to secure your systems from all sorts of different kind of attacks. People doing not only just trying to get in through your IoT device or your refrigerator to get into the network, but if you think of like city infrastructure kind of problems, if somebody wants to do some kind of attack which actually goes in and screws up your particular device, well then you need to have some type of larger system that does things like IP whitelisting, blacklisting, and that sort of thing. So when you think about your whole security aspect of an IoT device, you can't just think of just encryption on the core. You've got to think of the whole system, you know. And
The
so
whole stack, a layered approach.
yeah, so
and
it
an
needs to.
ecosystem
So a lot of
really.
that information will be done in the gateway, but it still applies to the edge device. So you still got to have that handshaking between the edge device and the gateway device to secure the whole system.
Yeah, that's a good point. So along with, that's obviously a technical requirement. What else about IoT in terms of the technical requirements is different moving forward than what we have been seeing?
Yeah. Well, I think the biggest thing is that it's a massive integration challenge across multiple domains. So you have, you know, in a typical system, you've got, you know, power management, MEMS, analog, digital, and RF, all on the same you know, edge device. And I think you're not going to find especially small companies that have expertise in all of those areas. And that's why IP is such a critical consideration. But even given IP, you've got to make sure that those things can actually be made to work together in the same environment or often on the same chip. And so that's really, I think, one of the biggest sort of interesting challenges of IoT is it's bringing all these smaller players in, and not just small players, but people who are new to the IC industry. So systems companies and cloud companies are increasingly getting involved in designing these type of systems because they're the ones who are going to make the big money out of it, and so they're focused on getting the right edge devices that meet their needs, often taking the tools into their own hands and becoming semiconductor industry participants in this process. And again, you know, they're coming at this from a system or cloud core competency, and we have to do, you know, in the EDA and the IP industry, do everything we can to make it easy for them to adopt these methodologies and really broaden the tent of what, you know, the semiconductor industry is today.
What are you seeing there, Jim?
Well, you know, as far as changes from traditional IC design way back, it's kind of a little bit back to the future. So, you know, especially with ARM should know this very well. I mean, when they started off back in the 80s and in the 90s, the chips were the ARM 7 TDMIs, and they were going into cordless phones and cell phones and that sort of stuff. So it was very low end compared to today, very low end processors. But then they started kind of going up the food chain, and you got to and you can describe it better than I can, the larger end processors, and now they're targeting, you know, data center type devices and big data type of processing. But this whole thing with IoT is kind of what I say going back to the future, in that now you're looking at Cortex M0s and M3s as kind of the major devices on these little small edge devices. So in a way, designing these devices is kind of how we used to do back in the 90s in a lot of ways. The difference is, though, again, is power management, because it's the necessity of having these things last a long time. You know, battery that'll last 2, 3, 4 years or more, We did a design that was on a water meter where the battery had to last 20 years. So, energy conservation and now even energy harvesting is such a big deal that power management with both the processor subsystem and the analog is very critical. It's very tricky. So that's the harder part of the design than possibly what we used to do years ago.
Yeah, and it goes, in fact, in the we have two movements. Yes, of course, we need to save more and more power. So it's work from the architecture to the actually optimizing the implementation. But we see also another movement, which is increasing the processing power in IoT nodes, because we can't really upstream all the data directly to the cloud and wait for the cloud to do something before
That's a good point.
before we have a result. And if we want really to have 1 trillion devices communicating, we need to have more processing locally. And this should be done with a very, very low power budget. So we are working on this problem as well, increasing the processing power on the nodes, but still keeping the power budget as low as possible. And for example, in our I talked about our subsystem, secure subsystem. We have in that subsystem started to implement things to help at an architecture level to help saving power. And the architecture, in fact, uses two processes. One which is processing the normal operations, so the background tasks, background processing. It can even be shut down when we don't need to have any processing and just counting until we need to wake up. But we have a second processor, which is then a processor that can run faster and that can really perform heavy lifting in terms of processing tasks. The thing is that when you start pushing the processors to the limits in frequency, this leaks a lot more because you have to use different cells, different VTs. So it's necessary to push a bit the technology, but on the other hand, it leaks a bit more. So that's why we have decided to have this dual processor architecture, because then in that case, you only power up the island where you have the second processor when you need to do the heavy lifting, and the rest of the time just switch it off, which means that you still have processing, but you don't have the all the leakage, all the consumption that is required by a higher end processor. So in the end, you get the maximum performance, but you get it only when you need it, and in average, the total consumption of your device is quite low because it's based on the leakage of the rest of the design, which is not really pushing the limit in terms of frequency.
Great.
Oh, so I think one other area to touch on, and I think this goes back to the Future in some ways, is the process nodes that a lot of the most interesting IoT designs are being done on are not the ones you might expect. A lot of these IoT designs are not going to TSMC N7 or something like that. We're seeing a huge number of them going at 180 nanometers. That seems to be the big, one of the big drivers of growth at this 180 nanometer node. Fabs like Tower Jazz and XFab really seem to be making a lot of hay out of this. And part of that is the integration of the analog and the RF and real world voltages into these things. They can support 200 volts at 180 nanometers. So, and we're also seeing a good amount of 65 and some 28 as well, when they're getting into especially that big dot little kind of stuff, it's more 28. But, it's been a bit of a surprise, I think, to a lot of people in the industry, the process nodes that people are settling on for these things. And I think a lot of that comes into, these desires for analog features or perhaps even MEMS features to be integrated into the process. Also just the, if these are relatively low volume designs, being able to get up and running on a process without a, 9-figure mask cost or whatever.
Yes, the economics.
The economics really do push you in that direction. But even for, we have a customer who makes TPMS sensors, and they've shipped 350 million of these things, yet it's at 180 nanometers because that's just what was the best choice for their particular combination of requirements.
In fact, it's interesting that these older processes are now very affordable, because that means we have the possibility to enable a new class of customers to build SoCs which were not able to do it because the initial costs were
Right.
quite high. And now it becomes economically viable to build a small series of SoCs because the mass set is cheaper, because we have introduced design start and the processor license is $0, etc. So it's complete set of factors that make it easier for companies to jump that step and actually go and build their own SoC.
And that shouldn't be the importance of the Design Start program really shouldn't be underestimated here in terms of both the cost of access but also the ease of access, right? And so I think that's something that these companies really care about is how am I going to deal with how am I going to negotiate as a peer with a company like ARM? Well, the Design Start program brings a fixed contract and an easy transactional business model to this environment, and I think that's as important as the $0 upfront cost.
Every step of the path to an SoC is simplified, including the legal and negotiation procedures. Yes.
Yeah,
And that's always. No, sorry.
Go ahead. Well, I was going to say, what I'd like to see it as well is, I mean, the Design Start program is really a good start, but I have to admit it's only part of the solution. If somebody's going to build a chip, he's going to need to have some type of flash interface or something how to boot the chip, or he's going to have some communication. So I really want to see the industry do more real reference designs, something that really gives the kind of an extension to the Design Start. And so I'm hoping we can do some of that. I hope others will do as well. And I think the trend is that more people are doing platforms and that sort of thing.
So along those lines, what exactly needs to be included in those reference designs?
Well, I think you can probably put in a number of different types of categories into the different types of applications, but there's a number of common things that are always going to be included in these low-end devices. You're going to have certainly a CPU. It's going to be an M0 or a CM3 type class. Then you're going to have probably some type of external memory, because internal memory is expensive and it can use a lot of power. That's a trade-off you have to worry about. Security is one. What security you put in there. Is it going to be AES? Is it going to be something like that? And then, of course, your communications link. Is it so there's probably a number of different flavors of radios and that sort of thing. Sensors, obviously, sensor interfaces. Maybe you need an I2. Kind of a new hot IP now is I3C. So you'll start seeing a lot of connections to external sensors with I3C. So if you kind of lump them together, you've got a processor subsystem, then you got radios that maybe you can interchange. Maybe you can design reference designs where you can pick maybe a Bluetooth radio or some other kind of radio. Maybe your sensor interfaces can be fairly common, maybe with using I3C if you use an external sensor interface, but if it's an internal interface, maybe it's some kind of standard ADC type thing. And then, of course, power management is something that's always going to be customized or customizable, but there are techniques you can do that you can kind of modularize that, so you can kind of build on that. So I think those are the key elements that'll be common, and then anything else from that is going to be the company's custom secret sauce.
Yeah. I agree with most of that, although I do think that providing end-to-end examples, including instead of saying, okay, well, here's a digital interface to your sensors, I think bringing some MEMS and bringing some analog on die is really where things are going to end up. So I'm hoping that we can come up with some reference designs that include the true end-to-end, because when you take apart like the TPMS sensor, that's one package. It's got a MEMS die, co-designed with an IC die that has all the analog, all the digital, and all the RF right there on one thing. And I think that's where these IoT devices are really going to end up if they're successful, is this very, very tightly integrated, customized and fit
I agree
for
with
purpose.
you. I agree with you 100% on that.
And I think we have to show people how to achieve that and how they can achieve that in these kind of reference designs.
Well, and the good news is that at least the digital part of what you described is basically the subsystem we have integrated in this new version of Design Start. And we even have something that is not really well known, but we have integrated even in Design Start. So for $0 license cost, we have integrated the minimum element that make a system secure, which is the true random number generator. This is the only part that cannot be done in software, and that has to be done in hardware. And we have included that in the package, if you want, to make sure that every IoT device can be secured as much as possible. So, and we have some interfaces, we have some peripherals as well to start working with the subsystem and expand it in the system. So yes, that's a very good point. We need to prepare the solutions. We need to also complement it with software to have a very good foundation to start designing. Yeah.
I'm curious where you're seeing the differentiation happening today with IoT and the opportunities for that based on everything that's available, all these design start kits and reference platforms.
Well, that's exactly what we enable with these subsystems, etc. Because when you design an SoC, if you spend all your time stitching things together, connecting your interconnect to the interrupt controller and whatever, you spend time and you don't really differentiate from the competition. So if everything, which is the basic horizontal stuff that everyone has to do, is already in the package, you just can concentrate on what makes the difference, what makes your system different, what is really interesting for an application, and that's really where you should spend your effort as an SoC designer. So it's really helping going in that direction.
So maybe I'll take that a little bit broader, which is to say that the differentiation in IoT is based on the services delivered based on the data, which is pretty far removed from the semiconductor content, although this, semiconductor content is absolutely a critical element in order to achieve that.
That's right. You design toward that goal, right?
So, but if you think about it that way, and you think about all the money that you're going to make based on services, the time to market becomes a critical pressure, more so than many of these other cost items that we've talked about. It's how can I get out there before the competitors and achieve all the network effects that come with that, rather than being sort of the also ran. So the market windows are narrow. Some of these are kind of, I will say, a little bit faddy, or sort of, but flash in the pan. You either hit that market and you took over the smart thermostat market, or else you missed it and nobody knows who you are. So it's very important to be fast to market, and so these kinds of things like reference designs, IP, quick negotiation, quick access to IP, quick access to tools, sometimes is more important than the actual costs of everything else. It's all about time.
Well, I think as far as differentiation on the chip level, on the edge device level, it's just two things: the analog, this is sensor technology for the specific data that you need to gather, and I think it's power management. Is how do you make that thing the lowest power possible for that particular application.
Well, and it's also about lowering the risk, right?
Mm-hmm.
And that's why we do third-party IP in the first place. What are some of the other challenges that we haven't discussed yet in terms of putting these new IoT systems together in with a custom SoC?
Well, I think we discussed it a bit earlier, but the real challenge is the variety of techniques that need to be integrated in IoT. It's from RF to embedded memory, sometimes to mixed signal, etc. And this requires complex interactions between different teams and different types of IP. It's something that will be a challenge. Again, we try to help here. We integrate as much as possible on the digital side. At ARM, we also have a wireless team that produces radio IP that is easy to integrate, and as easy as possible as can RF possibly be easy to integrate. And we try to take the perspective of digital SoC designers. So how to integrate a complex RF block as easily as a normal IP block. So that's clearly something that needs to be done to enable new teams to include RF in their design. But I'm pretty sure that for all mixed signal blocks, this needs to be done as well, because in IoT, if you want to have sensors, complex processing, etc., you need that as well.
Yeah, and just to build on that, I think there's a tremendous modeling problem that you have across these systems, because you've got different models at different levels of accuracy. But of course, your RF simulation model is not going to work on the time scale of your Cortex M0, embedded software testing and things like that. And so, being able to do all these simulations, make sure that the boundaries check out okay, and that these things are going to talk to each other correctly, and then provide the right level of abstraction that you can have confidence that when you get all the way up to the level of embedded software, you're still talking to your MEMS sensor correctly. The MEMS sensor is not going to interfere with its operation, and the RF is going to function, and all of these things, because you just have these wildly varying levels of abstraction. So being able to tie those simulations together in a meaningful way, I think, is one of the critical challenges.
You brought up a good point about the software verification. So it's very important that you get the whole thing to work with software in simulation as it's going to work in the real device. I mean, if you're just doing test software, that's not good enough. You really got to make sure it's going to work in the system.
So, you always think IoT devices are these little tiny things. I mean, is this always the case? I mean, you were talking about putting more processing.
Yeah, and it's not always small. It's Internet of Things, and things can be big things. For example, I talked recently with people working on the infrastructure market. So, including equipment to monitor bridges, to monitor tunnels, etc. And it's not that small, because you have many sensors, but at one point you have to gather the information from these sensors in local points, not having to stream that to the cloud, because you don't want to send vibration data to the cloud, but you need to understand what's going on in your bridge and what is not going okay. When something is wrong, you need to send that to the cloud. But when everything is okay, it's vibrating normally, you don't need to send any data. So this kind of processing needs to be done more closer to the edge. And sometimes they use nodes that are a bit more powerful to do this aggregation of data and do some kind of what we call sensor fusion and
spectral analysis
and pre-analysis of data. So this is coming, and I think more and more we will need to have more processing power to do some kind of analysis. And even if you think about cameras, right now we stream video streams directly from the object to the cloud or to the surveillance system. That's crazy. Since now we have computer vision systems that are able to identify faces, recognize people, identify faces, and just stream the information. Well, is it someone I know or not? And that's just one bit. So it's really really important to do this processing locally, because then we can do something much more interesting. And we can save power, because transmitting information is really consuming a lot of power. So it makes the nodes, in fact, much more efficient, even if you have more processing capability on the nodes.
Yeah, and just to expand on that a little bit, I think there's the three tiers of the IoT. It's a very interesting design challenge to decide where your processing is going to happen, whether it happens at the edge device, at the gateway, or truly up in the cloud. And I think obviously the service that you're going to deliver partly dictates that, and how much control you need to have over the service, because you really want you want to deliver your value proposition, and sometimes that can mean having a little bit more control over the data processing. Also, it's a heck of a lot easier to update your cloud processing than it is to update your edge device processing, right? So how much flexibility you need over time, how many new applications you're going to discover for your data. If you down processed it so much that all you found out is that there's 3 faces in the scene, and now you come up with a new algorithm that says, oh, now I can identify which individual people are there. Well, I don't have that data, so there's this interesting trade-off that you have to make between, as you say, power for transmitting this data and just plain bandwidth availability against what are you going to do now and what are you going to do in the future of this service, because that's one of the great powers of these things, is once you've deployed these massive and very expensive networks of edge devices, how do you continue to continue to build new and newly differentiated services based on the existing network of IoT devices?
Well said.
I have no idea what time it is, but do we want to take questions? Where are we at, Jeff?
209.
Okay. Do we have any questions from the audience? Don't be shy.
Come on, Sean. You have a question. I'm sure.
So with the IoT touching so many different areas, from healthcare to education to smart homes, smart cities, infrastructures, homeland security, and much more. And transportation, of course, which is a lot of it. The discussion is here on the IoT and autonomous driving. Will there ever be a real, true autonomous car? And that means, now think about it. Think about the insurance companies. Think about all the other things that need to be thought out, not just the technology, but through legal means, And I don't know.
So the question is, will you be able to drive your car by your insurance? Because you're less reliable than the machine. So.
Oh, I know. But some say it won't be a total autonomous switch.
Could it be autonomous means you can drive your car without the insurance company knowing about your car? Is that what you mean by autonomous?
No. But I don't know.
Yeah.
Is that any other challenges along those lines? I mean, legal challenges and.
Well, I think it's a funny topic because
Yeah.
I think there will certainly come a time at which autonomous cars have a better safety record than human drivers, right? That's pretty easy to anticipate. But on the other hand, something new always has interesting new liability consequences. If
Right.
I were proposing it today out of the blue that we were going to put a 50-gallon tank of flammable hydrocarbons in your car, you might say I was crazy, but here we all have gas tanks, right?
That's
And
right.
so the whole internal combustion engine people driving around thing doesn't sound like a great idea until it's been established as that's our lifestyle, right? And
Right.
so I think the autonomous car has such an incredible opportunity to really improve our lifestyles, to make our lives better,
Yeah.
and I have to believe that will win out over the lawyers in the end.
Good answer. Any other questions? Okay, I want to thank our panel here. Thank you so much for joining us today.